Hey guys, this is the physics nerd, and today we're gonna learn about what gravity is. So, in school, you guys may have learned that gravity is the attraction between two masses, or two or more masses. For example, us being stuck to the earth is because of gravity. And of course, gravity is not is the weakest force in the universe. That's why you need such large masses like the sun and the earth just for it to work. So, an example of this is in the sun-earth system where the sun pulls the earth inwards in in an orbit around it. And the reason the earth stays in orbit around it instead of going into the sun is because it has a sideways velocity, like a really high velocity of 67,000 miles per hour. And because of this, it stays in a bit of an elliptical orbit. It's uh, mostly circular. It's not extremely elliptical. So, yeah. And the equation for uh the gravitational for like the strength of gravitational force between two masses is G or the gravitational constant times the f the first mass times the second mass divided by the distance squared, the distance between the two objects squared. And you guys may be wondering what that G is. Like what's it there for? It's just a constant, the gravitational constant. Without it, it would just be that the mass 1 times mass 2 divided by d squared is proportional to F. And G is basically equal to 6.67 times 10 to the power of a negative 11 meters cubed per kilogram per second squared. And we can also see that gravity doesn't just help keep the Earth orbit around the sun and the moon orbit around the earth and stuff like that. It happens in many places in the universe and it doesn't have to be just orbit. And we'll talk about that in the next segment. So now, what are some other examples of gravity other than just orbits? Like the moon going around the earth and the earth going around the sun? Well, another example, wait, sorry, uh, of this could be the sun's formation. So we know that when the solar system formed, that most of the mass was just in the center, and there's a bunch of mass rotating around, of course counterclockwise, because that's how it started off in our solar system. And because of this huge clump of mass, which was just a bunch of uh, clouds of hydrogen, oxygen, and many more abundant elements that were found back then in the universe, uh, these all clumped up and started colla collapsing inwards. And because of this, pressure started forming, and subatomic particles like protons and neutrons started trying to fuse into each other, which created energy. And then because they collapsed in, it created a ball, kind of a ball of plasma, which is why our sun looks like is emitting so much light because there's it's a ball of plasma that's so hot that fusion happens within it. And we can also see this in the in things like the space missions we did, like how we got to the moon. So this to show that we can take the Earth, which is like over here, and we got the moon kind of far. Of course, this is not to scale. We're just drawing this. This is just a quick sketch. So we're trying to get from here to the moon. So what are we gonna do? We know that uh So what we did was the first thing we did was we looked at what direction the Earth is rotating in. It's of course counterclockwise because it's the same direction that the solar system was rotating in back when it was still forming and it was like a disk. And of course it has to rotate like that to preserve angular momentum, conservation of angular momentum. And we'll talk about that in another video. So because of this, we can use this as a speed boost kind of. And when we send a rocket into space, it'll have a speed boost. But now, how are we gonna have enough fuel to travel that far? Because it's not as near as you think. It's somewhere between 300 to 400,000 kilometers away, which is a really huge distance. So what we did was, it was not just the fuel. We mainly used gravity to our advantage. So once we got near to the moon, we would kind of start going into orbit for a few days. And then at a point of time, we would send we sent the lunar module down to the moon and kept our command module continuously in orbit because if both the modules are down on the ground, they're not going to have enough fuel to come back to from the moon to Earth because they're going to use most of it to get off the moon. So now that they have, so when they get back, they can do what they basically do is they do the same exact orbit, but they use a slight rocket fuel boost to get shot off towards the Earth. And when this happens, they then start orbiting around the Earth for a bit and then slowly use their parachutes and their heat shields to safely land on Earth in a spot. And yeah, these are just two examples. There's many more like let's say the Milky Way, which is a spiral galaxy. So we so it formed in a similar way to the solar system. So uh, but the only main difference is at the center of it is a supermassive black hole that we call Sagittarius A, A star. Can't color it black because the background's black. Yeah, so this is Sagittarius. I don't know if I'm spelling it right. A star. Sorry for my bad handwriting. So, yeah, and it's not just the black hole that's making this happen. Like the galaxy, it's not holding the galaxy together all by itself. There is just like how there's clumps of matter in our solar system near the sun, which cause the sun to form. There's clumps of matter around the black hole itself that contribute to the gravitational pull. And in the next video, we'll talk about how orbits work and theories that came to improve our understanding of gravity.